We are in geometry, lesson 2-1, our brand new unit, which has been updated on Khan Academy, so it's very new for me too. I've never taught some of the material here. Today we're talking about rigid transformations. Today's date is Thursday, September 17th, 2020. Our objective for the day is to do what? Charles.
Find measures using rigid transformations and identify preserved properties of rigid transformations.
There it is. Yeah, the first one is going to be pretty easy to do, and you'll see that for the homework and in the lesson. The second one is, it's kind of hard. We'll see. So let's get some vocab knocked out here. So vocab, rigid transformation. It's a transformation that preserves these two qualities, and it's all the time. It's the definition of rigid transformation. I talked about it a little bit last unit. Does anyone remember the two things that are always preserved? And Emma, I can't see your camera. What two things are preserved? One person knows. Yeah, what?
Is it source and image?
Good guess. Yeah, those two words do go with transformations. No, it's something else, and I don't see any hands. So let's go through this. I don't want to spend too much time on the notes today. The whole point is to give more time to do homework. It preserves angles, and I can say lengths, distances. I'll say distance and distance. Generally speaking, if I have some sort of shape and I do only rigid transformations, that shape will look exactly the same. It might be rotated, it might have a different orientation, it might be flipped upside down, but that same shape, it looks the same still. It didn't get bigger, it didn't get smaller, I didn't change the angles to make this right triangle turn into a 60-60-60 equilateral triangle. It still looks the same. And there's only 3 rigid transformations that you need to know. And I get to write them down, you don't have to. The 3 rigid transformations, you've talked about them before, there's only 4 that you know, so you have a 75% chance of getting it right if you just take a guess. I need 3 hands. What transformations do we know that you think are rigid transformations? Charles has already done the objective. I need more hands. Wyatt's already done a guess for vocab. I need more hands. You guys aren't even writing this down. Ulysses, go.
Rotation be one?
Rotation is one of them. Another. Kira.
But dilation?
Darn, dilation is the only one that is not a rigid transformation because dilation does not preserve distance. Dilation makes everything bigger or smaller. So it doesn't preserve distance, but a good guess. And then it's good that we get that one out of the way. Esha?
Translation.
Translation, yes. And Jade?
Reflection.
Reflection. These are the only 3 rigid transformations that we have in this class. Once you get into different sorts of spaces that are not nice and 2D on a plane, you're talking about, what about if you're on a torus, or if you're on a donut, what sort of rigid transformation? Like once you get in that space, it gets a little bit weirder. But for our class, you have only 3 rigid transformations, and it's kind of the definition of rigid transformations. A transfer or a translation, reflection, rotation, that is a rigid transformation. Okay, so this is a cool theorem. It's fun to say out loud. Maybe you guys can say it. You can stay muted and say it, but CPCTC, if you get them mixed up, is it CTPCCC what? It's CPCTC. Why? Because its corresponding parts of congruent triangles are congruent. And it is a mouthful to say, but here's the general idea. If I have congruent triangles, that means the triangles are exactly the same. I can copy paste that triangle. I might rotate it or something, but the triangles are congruent. So let me go ahead and draw a triangle. I don't want an isosceles triangle. Let's make something a little bit weirder. That kind of looks like a right triangle. But if I take this triangle and I copy paste it, yeah, I can translate, I can rotate it, I can do whatever, but it still looks the same. It is the exact same copy of that triangle. I just did those 3 transformations to it. They are still congruent. If they are congruent, I'm saying, then their parts are also congruent. So we're all making the assumption. We're saying our giant if right now is that the triangles, maybe I can abbreviate here since it's just notes for me and you guys. If the triangles are congruent, then the parts are congruent. So I'm now telling you, hey, these triangles are congruent. Well, then that means that this angle must match this angle. This angle must match this angle. This side length must match that side length. Those pieces are all congruent. All of those angles are. I didn't have time to annotate all of them, but you can assume all of those angles and all of those line segments are congruent. They're exactly the same. And you're like, well, duh, that makes sense. If they're congruent, all of the parts are the same. But once we start writing proofs, you have to memorize CPCTC when you write out your proofs for your tests, your quizzes, and your homework and stuff like that. Not today, but in the future. Okay, so now we're finally able to prove congruence after I say this. If you can map, wait, map? What is he saying? Write out a map, draw a map of North America? No, map in geometry means I can move one thing onto another. Like if you have some tracing paper and I lined up one piece on the top with a piece on the bottom and they match exactly, that means I have mapped one shape onto the other shape. So if I have, maybe another synonym for map is match. If you can match one shape onto another shape, or if I can, maybe move is a better word. I'm going to change this to somehow move. Technically, I should be saying like translate or rotate, some sort of transformation. If I can use transformations to get one shape onto another, only using, what word have I defined? Keep your brains active. Brains active. What word have we defined? What's up here? Only using, someone new. Prove to me that you don't need to take notes. Prove to me that you're paying attention. Ugo, what's a word that we've defined before? Some sort of movement word.
Congruent. Corresponding.
Congruent is an adjective that just means the same.
Corresponding.
Not quite. I'll give you the second word. It's transformation.
Rigid.
Yeah, there it is. Thank you, Ugo. If I'm using only rigid transformations, I guess plural, then the two shapes are congruent. If I use a dilation to get there, hey, they're not congruent. But if I only use reflection, only use rotation, only use translation, if I only use those three properties and I can get one shape on exactly on top of the other and they perfectly match, then that will prove congruence. All right, hopefully I'm not doing something mind-blowing. It's like, maybe this is common knowledge, Mr. Snell. Get on with it. Okay, here we go. So the other thing that you need to know that I eventually will prove, and it's kind of silly that I have to say this right so early, is that if I look at a triangle and I add up the three inside angles, so here's a triangle, chunk, 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 right? If I add up this angle, and this angle, I'll say this is angle 1, 2, and 3. If I add those up, 1 plus 2 plus 3, they always add up to, you've seen this in 8th grade before, hopefully. How many degrees? These add up to how many degrees? You've seen this, hopefully, please, before. Wyatt?
180 degrees.
It is indeed 180 degrees. Yeah, so 1 plus 2 plus 3, those add up to 180 degrees. There's only one problem on the homework, and you might not even get this problem on the homework that you'll need this knowledge for, so I just want to throw it out there just in case you haven't seen it before. Kira has a question.
Yeah. So 1 plus 2 plus 3 is the same as like angle A plus angle B plus angle C.
Yes, I'm not being very formal. Maybe I should be more formal, so I should come back here and say.
Yeah, that would just make more sense to me because 1 plus 2 plus 3 is 6.
That is indeed correct. I'll call this angle A, B, and C, and I'll say the measure of angle A plus the measure of angle B, and you need to move out of the way, plus the measure of angle C is equal to 180 degrees. Yeah, keep me honest, keep me exact, because I am a mathematician and I need to be exact, because we can be exact. We're the one area in school where it is black and white. There's no, you could have used a different preposition. No, it needs to be the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees. If you forget that degrees, then you're all of a sudden in radians, which is a problem. All right, so let's do an example. So I have a triangle ABC. There it is, that blue triangle down here. This triangle ABC is translated 8 units to the right and 2 units down. It doesn't matter that you know where it's going exactly, but hey, I'm translating. I'm using a rigid transformation. And I create triangle A prime, B prime, C prime, which means these two triangles must be congruent because I've used a rigid transformation. Okay, my question for you. What is the length of line segment A prime, B prime? This is kind of the just getting warmed up question. This should be one of those easy ones, I'm hoping. If these two triangles are congruent, using CPCTC, congruent parts of congruent triangles have, oh man, I already messed it up. But these two things are the same. What must A prime, B prime, that line segment, what must it be? I need to hear from someone new. Who have I not heard from today? I think Emma and Hazi, right? Right? Yep. All right, one of you two. Who's it gonna be? Length of A prime, B prime. Go for it, Hazi.
Is it 4.4? Because it just
is in, oh yeah, sorry. So, yep, you're right. Yep, 4.4. Nice. Yeah, because yeah, that part should match that part. This part should match this part. So Emma, just tell me so I can get your participation out of here. C prime, B prime. What's the length of C prime, B prime?
3.3.
3.3, exactly. 3.3. All right, so we understand the basics. Like, yeah, those two triangles are the same. Okay, well now how do you use this in a little bit more sophisticated way? Let's look at example 2 down here. So in this image above, and maybe I shouldn't use image, maybe I should use picture, because image is a specific word in geometry that means I have done some sort of transformation. So let me change this to picture. In the picture above, what is the measure of angle CAB? CAB, and I could have just said, another way of saying this is the measure of angle A. But CAB means I go from C to A to B, and I'm always talking about this middle angle. So measure of angle A. So A is right here. Oh, darn. A doesn't have any measure. Oh, okay. Well, B does. And so does C prime down here. How are we going to use only those two pieces of information? I know what B and C prime are, but how am I going to get to A? What the heck is going on here? A lot of people have hands raised, which is awesome. You guys are thinking. And I can call on anyone again because everyone's in. Yeah, Kira, go for it.
Okay, so I think we know that 180 is always going to be the total, and then to figure out angle A, what we could do is 97 plus 34 equals what? And subtract the answer of that addition from 180, and you'll get angle A.
Okay, so 180 minus whatever that x is, that will be the measure of angle A. Did I write out all of that work correctly? Okay. Everyone else, can you follow her work? Give me a thumbs up or thumbs down. Does she need to re-explain or not? Can you follow her work? Thumbs up, I can follow her work. Thumbs down, I need another explanation real quick. Just waiting on Emma. Okay, Emma, ask a question so that Kira can re-explain.
Well, oh wait, I think I just read something wrong. I'm good.
Okay, and just in case, Kira, can you re-explain it one more time?
Yeah, so like you're getting, since these triangles are the same, you could just put 90, like triangle, like this prime one on top, and you'd see angle C is 97. And so you already have two of them, and that's where you're getting the numbers, and then you're just gonna add those two together and then subtract x from 180.
Cool. All right. So I need another volunteer to actually do that math. That was an excellent explanation. I love the fact that you set it up without actually doing any of the arithmetic. That's perfect. Now I'm going to let someone else do the arithmetic. Yeah, Charles, go for it.
Well, 97 plus 34 is 131. And then 131 minus 180 is 49. So angle A
You said
is
it a little
49.
bit backwards, but yeah.
Well, okay.
I think you said 131 minus 180, but it should be
Yeah,
180 minus 151. Yeah, but you're good.
Yeah, I
149
never
degrees, and we're done.
how to say that.
You're good.
I just
And we
tend to
box our
say
work.
it.
Cool. This is 5 up through example number 2. I'm getting 5s, 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 4s, 5s, 5s. Nice. All right. So I'm going to continue on to the kind of the bread and butter of today's lesson. This is going to be tricky and it's going to take a while, but it's fun. I think it's fun, at least. Hopefully you guys will think it's fun too. So you are going to help me, and hopefully you have a piece of paper still to do some scratch work, because you're going to need to draw for this one. You don't need to show me your work, but I need you to have some sort of way to express yourself other than just purely doing it mentally. So get out a piece of paper, get ready to do some drawing. You're probably gonna have to do a drawing for every single one of these cells. So that's 1 drawing, 2 drawing, 3 drawing. How many of these? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 3. You're gonna do 27 little sketches here. They don't have to be pretty. And definitely coming from me as a not the best artist and growth mindset, I can just do better if I try. 27 drawings. Here we go. Okay, so for each of these statements, you're going to say always, sometimes, or never. You're going to say this statement is always true with a translation, or it's always true with a rotation. It's always true with a reflection. Maybe it's a sometimes true. Sometimes it is, sometimes it's not. Maybe it's a never true. This is impossible, Mr. Snell. We're going to make another assumption here that I forgot to write down. The assumption is you're not doing the identity transformation, which means if I'm doing a translation, I'm not translating 0 amount. No, translate at least more than 0. If I'm rotating more than 0 degrees. That's silly. Because otherwise the answer to all of these would be sometimes, sometimes, sometimes. What if I translate by 0 degrees? Okay, those are silly. We're going to throw those out. And assuming the reflection, there's not really an assumption that we make there. Like if you're reflecting that you have to reflect. I'm forcing you to reflect. It's not like you reflect by 0. Like you have to reflect. So the only assumptions are that we are not translating 0 amount and we're not translating 0 degrees. Those are 2 assumptions. We're not doing any identity transformations. But that's it. I can choose.
Would 1 be the same as 0?
What do you mean 1?
Like if you translate by 1.
If you translate by 1, that means I still have moved 1 unit. I'm a little
okay.
bit left, but I am not where I was. Yeah.
Okay.
Oh, yeah.
Makes sense.
That's a good point to make. Yeah. Translation is addition, not multiplication. Perfect. Yeah. Kira, question?
I don't really get what you're wanting us to do here.
I think it'll be clear once I do a few examples because these are hard to get going. But can I do like maybe the first 2 with you guys? Okay. So angle A and angle A prime. There's no diagram, Mr. Sindel. How am I supposed to do this? You make your own diagram. Can you make a situation where under a translation, I abbreviated here because I didn't have enough room for my table. Under a translation, some 2 angles have the same measures. Okay, well, I'm going to go ahead and draw down here. Let's draw, I don't know, a triangle and another triangle. I moved this triangle down this direction. Okay, maybe I chose that angle to be A and that angle to be A prime. Did those 2 angles, are they congruent? They said that they have the same measures. Well, yeah, those 2 have the same measures. So I'm thinking it's either a sometimes or always. It's definitely not a never because I've just drawn a sketch of when it does work. So now I'm thinking, okay, it's between sometimes and always. I can't tell. Okay, so maybe let me try drawing another picture where I break that. If I can break it, then it's a sometimes, right? Sometimes is, sometimes isn't. And I'm thinking, okay, with just a translation, just moving, and maybe I can even copy paste this guy. Just by moving this around, is it possible just by translating it around to get this angle A, which will turn into A prime, to be a different angle? And you are probably clearly seeing on my screen, like, no matter how you are dragging this around, that angle A prime, I guess, is not going to change angle. This is an always true. No matter what happens with angles under translation, this will always have the same measure. So I'm going to put an A here. Oop, I need to go back to my head. An A. Angles under translations always have the same measures. All right, you guys want to try another one with me? I can
Wait,
skip around this table.
all of these like
Charles, don't
be...
give away! Don't give away! Don't give away! Yes, I know. I think I know what you're about to say. I'm starting off easy, and you guys are seeing the patterns already, and that's awesome. But don't ruin it for your peers.
I mean, I
let
kind
me
of
skip-
realized it when I saw that there's only 3 translations.
3 translate. I don't know what you mean by 3 translations.
Translation, rotation, and reflection. Those 3.
Oh yeah,
just
I mean
those 3.
we're only dealing with rigid transformations, and if you go back to the definition of what is a rigid transformation, they have 2 things in them: angles and distances. So whenever you're dealing with those 2 things in our table, you might have an answer that is pretty straightforward. But again, I'll let you guys play with this. You need to help me fill in the table. I want you guys to play with this for like on your own for a bit. But let me jump around on the table. I don't have to do rotations and reflection unless you really want me to. Let me jump down to Perimeters. This one is fun. Let's play with perimeters. And perimeters turns into circumference down here. So this answer and this answer should be kind of related, you would think, right? One's dealing with circles, the other one's dealing with maybe a triangle or a square or something. But they should be semi-familiar. Okay, so let me deal with perimeters. Let's do this cell right here, a rotation. If I am rotating and I have two triangles, can I make their perimeters not the same? And maybe you can even do this. You could probably do this mentally. Okay, I have two triangles. I'm going to rotate them. Just by rotating them, can I change their perimeters? In your mind's eye, can you tell if this is an always, sometimes, or never? So I'm giving you guys another 5 seconds to think, and then we're going to vote as a class. So if I'm rotating triangles, and maybe my perimeter was 3 or something for my first triangle, is it possible to get a different perimeter just after a rotation? Okay, so what we're going to do is we're going to vote. I wish I knew sign language to do all of the A. I know A is this, I think. I don't know. We're just going to vote 1, 2, or 3 because I didn't learn my sign language. 1 is always, 2 is sometimes, 3 is never. In your cameras right now, hold them up. Let me see.
So always is like you can always change the angle of it. I mean the perimeter.
Always means it is always true, I guess I should say. So the perimeters are always the same. And let me see your guys' screen. So for perimeters, I'm seeing ones always. Everyone's saying you're in agreement. Darn, okay, so no one, I can't have any conversation then. But yeah, it isn't always true because is there someone that can maybe give an analysis for a quick way of knowing, oh, well, this is why it's always true without going through, well, if you rotate it this way, rotate it this way, there's one quick way of saying, oh, just by the definition, it's always true. Can someone explain it that way? Esha?
I don't know how well I'm going to do this, but I just think of it, the way I think of it is you can rotate it any which way you want, but like no matter what, it has to be the same size in your rotation. So it can't change.
Yeah, exactly.
Perimeter can't change.
Yeah, does anyone have a different way of explaining it? Charles, you've been waiting patiently. Yeah.
Well, the definition of rigid transformations is it can't change like the size or angles or anything. And rotation is one of those.
Yeah, so distance. Distance is part of our definition. So any single time in this table that you see something dealing with distance, like perimeter, that is a distance. Distance that I walk around the outside if I was like a microscopic ant or something. This is dealing with distance. I'm going to write distance in my notes for you. Distance. Oh, if it's distance, then you know the values for these two as well. Because it's a rigid transformation, this has to be an always, and this also has to be an always. But let's play around with it in your head. Make sure that you visualize them. Okay, translating doesn't change perimeters. Reflecting doesn't change perimeters. So what I'm going to do now is I'm just going to let you guys play with this. Give you guys a few minutes to play with as many of these cells as possible. We only have 7 minutes left, huh? I wish we had more time in class. If we had like a 53-minute period like we had before, you guys would actually be able to play with this. But unfortunately, I have to kind of persevere. Let's go through these a little bit fast. Angle A and angle A prime have the same measures. Rotation. Give me answers 1, 2, or 3. Take a guess. Always, sometimes, or never. Get a sometimes. I can get a never. All right. And the answer here is an always. Why? And I'm going to ask one of you to, again, use the definition somehow to explain why.
Well, we know because of CPCTC.
Yeah, and they're congruent. Yeah. So that's only dealing with triangles though, right? What if I was dealing with a square? What if I translated a square, then CPTCC, then CPCTC would not apply because that only applies to triangles.
Then you can still say that there's a rigid transformation going on, which describes that you can't change the angles because you're not increasing or decreasing the size of that square.
Okay, yeah, and there you go. So this is dealing with angles, and since each of these is a rigid transformation, rigid transformations cannot affect angles. So it seems like everything in here is going to be an always. So let's try to find something that's a sometimes. So I'm going to write the word angles on here, which is one of the two properties that is always preserved, so that all of these have to be an always. Ooh, coordinates. Coordinates is not an angle and it's not a length. It's just a point. So I'm going to guess here that maybe we're going to get a sometimes. Let's go ahead and look at this one. Translation. B and B prime. You can just use a point. You could use a point on a triangle. You could use a point on a square, but a point. If I translate the point, is this going to be, again, we're going to vote. Always 1, sometimes 2, or never 3. What are you guys thinking here? You're doing this in your mind's eye, or you can do it on paper too. That's why I told you to get out the paper. A lot of people are putting 3. Some people are 2 or 3, and it is 3. Yeah, because we're assuming that you can't translate by 0. So this one is a never. And on Khan Academy also, they're not going to translate by 0. Oh, so I did never. Okay, I didn't do 3. There we go. Okay, what about a rotation? This one's gonna be a little bit more fun. I'm seeing a 3. I'm seeing a 2. I'm seeing a 3. Interesting, interesting. Which one is it and why? Jade, talk to us.
I think it's
You put it
It
up at
was
2. You
kinda-
said sometimes.
yes,
Why is it,
but then
why? I'll tell you what. You're
Because-
correct, but why?
because if you're rotating it, your points are gonna change. But you can also rotate it by an angle, or you can also rotate it by 0. So,
Oh, no, no, no. We said we can't rotate by 0.
oh,
You can call someone else if you need help.
well, I don't know. Okay, let's see. Kira.
Well, I was thinking, what if you rotated it by 360 degrees so it lands on top of itself?
There it is. Yes, if you rotate by 360 degrees, that's not rotating it by 0 degrees, and therefore it's sometimes. And I know there's going to be someone nitpicking. You said no identity transformations, and technically 360 degrees is an identity transformation, but I forgot to write it down, so you are 100% correct. It's a sometimes. But assuming that we can't do 360 degrees or 720 degrees, any multiple of 360 degrees, then this would be a never. Yeah, but because I forgot to say that, it's a sometimes. What about reflections? 1, 2, or 3? Reflections, 1, 2, or 3? Ooh, some people are doing 3, some people are doing 2, so this one's gonna be fun again. I want to try to call it someone new. Ulysses, you've been patiently waiting. You've been trying to answer. Let me give you a chance. Yeah, go for it. Why'd you say 3? Why'd you say never?
I said that because I was like, either way, I feel like whenever you'd reflect it over a point, the point, like the coordinates would always change.
Okay. So what if I told you that it was a sometimes? Could you think of, and I don't want to put you on the spot, so you don't have to answer. The answer is actually sometimes in this case. Can anyone think, and I'm going to give you first priority, Ulysses, if you can think of it. Can anyone think of an example where I can reflect and not move the point? I see only 2 hands. Yeah, Ulysses, you get priority. Go for it.
Yeah, I was like, I didn't see that it was just B, so, because you could like put the line of reflection could be over B, and
There it
stay in the
is.
spot.
Nice, yes. And that's the one case where it won't be a different coordinate. So again, he said, if I have B right here on the line of reflection, then B is also going to be the same coordinates as B prime. Perfect. And again, the whole point of this activity is you need to play devil's advocate. We're running out of time, so I might have to finish this video recording later. But let's do areas. Areas, same for translations. I'm on this cell right here. If I have areas of 2 triangles, if I just translate those triangles, what do you guys think? Always, sometimes, or never? 1, 2, or 3? And you guys are, the majority has it. It is an always, and I have to give the explanation because we have a minute and 20 seconds. If distances are preserved, then the sides of the distance for squares, triangles, or whatever are the same, and the formula for area just multiply the sides, which are the same. So it's an always. And because areas are derived from distances, All of these are going to be an always. Distance is the thing that creates area. All right, down here, line segments. Oh, I'm talking about lengths. What do you think? All three of these are the same answer, and they're all 1. Yeah, because lengths are one of the properties. So always, always, always. A, B, oh, this one is hard. Now we're getting into the hard stuff. I only have 40 seconds left. Let's just talk about this one. I'm doing a translation parallel. Can you ever have a translation where there is a sometimes maybe? It's either a 1 or a 2. It's definitely not a 3. Because like, what do you guys think? This one is actually an always. I challenge you to try to make a translation that doesn't have something parallel.
I don't really remember what.
Oh, because you can't rotate it.
You can't rotate.
Right.
It's just a translation. Exactly.
Oh, okay.
Okay. I'll finish this video later, and I'll try to have a mini picture for each of these just to make sure that you guys got them. But yeah, these are super fun, and this is your homework. So I've kept you for 5 seconds over. That's the end of the temporary notes that you have. Watch the notes later. Do the homework assignment. There's 2 of them. Kira, do you have a question before we leave? Nope. Okay. Give me a quick fist of 5 before you guys leave. Quick fist of 5. Where are you guys at for the lesson today? 4s and 5s. Awesome. Thank you guys. See you tomorrow, or see you later. All right, we left off right here, I believe. I made a mistake by recording only my face instead of this document. This is definitely now recording the document. A, B, and A prime, B prime are parallel. Okay, so if I'm thinking of a line, just this most simple shape I can also do a triangle, but if I have a line and I drag this line around, this line, and maybe if I copy and paste it, this line and the if I move this line off of itself, it's always going to be parallel no matter how I translate it. So this one is going to be an always true. Those are always parallel. And then the rotation. So again, if I rotate this, okay, so the lines are the same. Now, if I go ahead and decide to rotate this line, obviously it's not the same right here. But if I were to rotate this maybe by 180 degrees, come back over here and line it back up with itself, it is the exact same line, assuming that its center of rotation is the center of the line. So this is actually a sometimes true. So 180 degree rotation is my example there. And it's kind of, you don't really need it for the notes, but you want to be thinking of 180 degree rotation. And then for this one, a reflection, it depends on the reflection, right? So let's go ahead and say that my line of reflection is this blue line. Maybe I should make an actual line. I have the tool for it, right? Let's say I have an actual line. Let's make this size 2 for my width. Let's say I have an actual line. This is my line of reflection. If I have some sort of line that I want to reflect, let's make that black. Some sort of line that I want to reflect, and it reflects over here. Okay, yeah, those 2 lines are not parallel, which is what I'm looking for. But they can be parallel if I had this line. This line right here. This line is going to turn into this line, whoa, over here, and these 2 lines are parallel. In fact, not only are they parallel, they're on the same line, which is kind of cool. Another way that we can think about this, what if I instead started with a line that was parallel to the line of reflection? If I did that, then I reflect it over here and I get the same parallel line. So there's actually 2 cases where this is a sometimes. So sometimes, and I'll do the symbols parallel and perpendicular. Those are the 2 cases where parallel to the line of transformation or line of reflection. A, B, and A prime, B prime are both perpendicular to the y-axis. Okay, so really what this question is saying, if they're both perpendicular, or that means that they're both the same, they're both parallel, they're both the same slope, I guess I'm saying. So let's go ahead and draw out a graph. So boom, 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 let's draw out a graph that looks like this. And ignore these lines here and here. Okay, so there's my coordinate plane, right? My graph. I'm going to draw a line that is perpendicular to the y-axis. I'm starting off with AB that's perpendicular to the y-axis. Boom, that is not the line that I want. I want this line right here. This line right here is now perpendicular to the y-axis. No matter how I translate it around, again, I'm dealing with this first cell here. No matter how I translate this line around, I guess I should maybe do the image different from the source. No matter how I translate this around from the source, it is always going to be perpendicular to the y-axis no matter what I do. Even if it's over here, it's a line which goes on forever, it will be an always. So come back over here, say this is always. What about with a rotation? So with a rotation, yeah, typically it's not going to be the case where this works. So like if I drag this back to the original spot, if I rotate it, okay, yeah, it's no longer perpendicular. But again, if I rotate it by 180 degrees, bada bing, bada boom, it is exactly the same line basically. So yes, it is a sometimes. Sometimes yes, sometimes no. So sometimes, again, we have to worry about that 180 degree rotation. What about for a reflection? So if I am perpendicular to the y-axis and I start perpendicular, no matter, ooh, this one I actually got wrong in the last video. I thought it was an always, but it's a sometimes, right? So what if my line of reflection is something that is diagonal? If my line of reflection is over here, then my image is gonna flip down something that looks like this. It's kind of hard to see, but this is the mirrored version of this. This is no longer perpendicular. In fact, it's parallel. If I change this line like that, and this line comes down like that, and it should be exactly the same distance away, but there it is. So this is a case where it doesn't work, but notice that if my line of reflection is my y-axis, then yeah, I'm reflecting onto itself, and that is a sometimes true. So I come back over here and say this is sometimes true. Again, if my line of reflection again is parallel or perpendicular, I have to worry about those. Actually, perpendicular doesn't work, only parallel works, parallel to the line of reflection. The circle circumference. So circumference is a distance word, the distance that I walk on the outside of the circle. So I'm gonna write the word distance in my notes. So distance in general isn't always, always, always. Another way of thinking about this is the formula of circumference or the formula of area is dependent upon tiny distances. If you remember from 8th grade or whenever you did circumference, circumference is equal to 2 pi r. Pi is just a number. 2 is just a number. The only thing that this really depends on is r, radius, and radius is, again, just a distance. Distances are preserved in these rigid transformations. Therefore, circumference is also preserved in these rigid transformations. So what do we have down here? Our last and hardest problem. Line segment AB and line segment A prime, B prime are on the same line. So how do we do this? So let's go ahead and draw out, I have some, let's get rid of these in our notes because we don't really need them anymore. And I guess I can get rid of these too, don't need them anymore. What if I have some sort of triangle? Let's draw out a triangle like this, chung, chung, chung. If I have that triangle, the line that I want to look at is this, oh, we'll do yellow, orange line, whatever this line is. So I know it doesn't match up exactly because my triangle is not perfect, but this triangle, if I translate it up, it's no longer on that orange line. So it's not always true. And if I translate it along the line, in the direction of the line, then yeah, that line or this line segment down here, I'm going to call it AB, is still on that line. So this is a sometimes true. So it depends on how I drag it. If I go in the direction of the line, it does work. What about for a rotation? So if I rotate this triangle like 45 degrees, then the triangle boom, comes up here, and yeah, this angle is 45 degrees or whatever. Yeah, it doesn't work, right? But again, I have to always worry about that 180 degree rotation. If I rotate it 180 degrees, then the triangle comes down here, and this line segment is still on the same line. So I do have to worry about that, and it is a sometimes, again, worry about the 180 degrees. What happens if I do a reflection though? So obviously if I do a reflection, let me do a new line, because I have 2 lines, one on the same line and one for the line of reflection. Let's do my line of reflection as green. If I reflect over this green line, then our new triangle looks something like this, where it's down here. And again, this line is not on the line that I started with, that orange line. But if I move this line of reflection, this green line, to be the line that I started with, then hey, lo and behold, it is the same line that I started with. So again, it's sometimes if the line of reflection is the line that I'm talking about. So this is a sometimes. So this is really tricky if I ever am talking about the same line. You have to go back and check, like play devil's advocate. Does it actually work? Does it not work? You have to be the most careful. This is the only one with 3 sometimes over and over again. All right, so there's our finished table, and that concludes the notes.